So I am Devraj Singh. I am a BTech third year aerospace engineering student at IIT Madras. So the project assigned to me was the river and flood module for the tropical major basins, where we will be focusing mainly on the five basin deltas, namely Mahanadi, Godavari, Krishna, Irrawaddy, and Ganga Brahmaputra Delta. So these tropical deltas face some of the unique challenges that are present that are different in the temperate regions, such as extreme monsoons and the climate variability that can make them very flood-prone regions that are present there in the Asia. So what our flood module will try to achieve is finding the what how deep the flood will be and what will be the extent of the flood for a given discharge. So to design a flood module, we need few parameters to start with. So the first parameter that we'll be needing is the digital elevation model. So for this project, we use the FEPDAM, which basically removes the forest and buildings out of it, because we can't directly use the satellite data, as the water flow will be determined by the surface that is present there and its elevation. The second thing we will need is the width of the river. So that for that we are using the GRWL data sets that is there, that will give us the river center line and the width of the river. Now combining these two will form the backbone of the bathymetry that we'll get. Now third thing we'll need is the water discharge and the input points where we want to make the water inflow. So for that, we need some boundary condition that we can get using the historical data sets. For that, we are using the GLOFAST historical data set for last 20 years. What are the water discharge present in these rivers? And fourth, of course, we have our model, list flood model, which is the physics-based model for water flow. So to start with, we need to get the boundary condition. So using the last 20 years of the data set, we'll extract out the three discharge values, namely Q10, Q50, and Q100, which will basically give Q10 is basically the discharge value above which there's only 10% chances that water discharge will go above it. So if to give an example for here are some values. So if we have 28,000 Q10 for Mahanadi, then there are just 10% chances that the water discharge will go above it. Q50 means 2%, so there's just 2% chances that water discharge will go above it. And Q100 means only 1% chances. So this is like the rarest of the rare flood that might occur once in 100 years. So these are some of the flooding parameters, initial parameters that we started with. Right. So as I said, we have downloaded a data set that gave us the river width. But the biggest problem of that we face is that to design the river bathymetry, we need the depth of the river that we don't have. There's no open data set available that can directly give us the depth of the river. So to go about this problem, we need to carve out our existing digital elevation model to get the right depth. Now we can't get the precise depth, but there are some few research paper available that gives us some formulas that relates the width and the depth of the river. So using the width data set that we already have, we calculate the depth of our river and then carve it out of the digital elevation model to get the final bathymetry. So these are some of the steps that we follow on our existing digital elevation model. So it's like going about finding the imposing the width on the digital elevation model and finding the depth, and from each point carving it out, carving that much of reducing the elevation at those points to get the right bathymetry that we need. Right. For the last step, we need a few files to start with. For example, first we need to define what are going to be our water discharge. So we have found we are going to perform it on these three values for the five deltas. And next thing we'll need are the input points where we want to make the water inflow. So that we need to give in this some of these files, so-called .bci file, where give the coordinates of our points where we want the water to inflow. And then we compile this all together and execute the list flood model on this. So if I can just show you an example, this is the Q10 simulation that I did. Each stamp is showing 12 hours. So we can make it simulation even better if we change the timestamp, but then it will take a lot of time to perform each data set. That's why I perform it like day wise, 24 each varies for 24 hours. So this is Q10 for Ganga Brahmaputra Delta. After performing these on the other river also, here are some results that we got. Before directly putting that on the map, we have to do a little bit of filtering. removing, for example, 0.05 meter, because even the small values will be shaded in the purple region that might show that it's flooded, but actually the water level is just so minute, or maybe some error here and there, that it is insignificant. So removing those small values, this is the final result that we got for Godavari. So the first one is Godavari Q10, which is like the 90% probability discharge. Second is Q50 and fourth is Q100. Now, as you can see, the flooding region increases as we go towards Q100, because the water charges decreases, and this is like the flooding once in 100 year, once in a 50 year, and once in a 10 year. Same way, this is for Mahanadi Delta. This is respectively Q10, Q50, and Q100. Each again, we can see we just applied some better visualization, like putting a set like Google Map kind of thing in there to make it better visualize for us which cell will be flooded and which will be fine. So again, all right. So what are some of the limitations that we have with our project? Now, apart from some of the common error that we can have, like in the digital elevation model here and there, the biggest problem that, as I mentioned, was there's no exact depth data that is openly available. So that we are calculating using a mathematical formula that can give a lot of variation from the real depth that is actually there. Second thing is, while we because I downloaded the data of the last 20 years to find my Q100. It's not ideal to use only 20 years data to get Q100, but because of each data set costing like 2 GB of the data. So the problem that I got is we cannot have data more than of 20 years. So Q100 is kind of extrapolated data, so it might be a little bit offset here and there. So we can get maybe rather than 20 years of data, we can get that 40 years of data and calculate the Q100 in a better way. Last thing is, it's a small changes, but let's consider a friction factor that is called Manning's friction factor. We consider it to be constant throughout because we also don't have any data set available for it. But for water flow, it does not make that big significant difference because friction factor don't contribute that much. So I think that can work. Yeah. So finally, I like to conclude with the stakeholders that we have. The first stakeholder is obviously the disaster management authorities. For example, NDRF, who needs the flooding region in the case of some climate hazard like flood or a cyclone or something. So in that, this can be really helpful. Then again, local communities can be really helpful because they know what are going to the flood prone region where they want to maybe make their house, or how the then urban planning also, like municipality, sorry, where they have to focus more on this. And then lastly, of course, agriculture, because the water layer can literally kill the crops because it hinders the oxygen supply to the roots of the plants, so it can destroy the crops. So it will be helpful, it can be helpful for the farmers also. And of course, climate change adaptation, because the water discharge is directly dependent on the how glacier melts in most of the cases. So the water discharge variation that we'll got uh, can also indicate what is the condition of the glaciers that is currently, like what's the condition of the glacier right now. So yeah, thank you for, I like to conclude here.